In the last class, we studied about a predictor-corrector method by Euler. Euler's method, which solves the initial value problem dy by dx is equal to f of x comma y when an initial condition is given at x naught as y of x naught equal to y naught. And if you want to obtain the solution, say at a point x1, which is x naught plus h, then Euler's method says y1 is y naught plus h into f of x naught y naught. So, typically if the information is given at xn as y of xn and that is equal to yn, and you are asked to compute what yn plus 1 is, then Euler's method says yn plus 1 is yn plus h into f of xn yn. Then we also saw a modified form of Euler's method in which the curve, solution curve in an interval xn to xn plus 1 is approximated by a straight line passing through xn yn and having its slope to be the average of the slopes at the point xn comma yn and xn plus 1 comma yn plus 1. And so, we obtained modified Euler's method given by yn plus 1 equal to yn plus h by 2 into f of xn yn plus f of xn plus 1 comma yn plus 1. And we observed when we derived this formula that the unknown yn plus 1 appears not only on the left side, but it also appears here, and we need the value of the function at xn plus 1 yn plus 1. But our goal in deriving the method was to obtain what yn plus 1 is. So, this suggests that we can use the value of yn plus 1 here as that is predicted by the Euler's method. So, I call Euler's method as a predictor, and I use this predicted value of yn plus 1 and find what is f of xn plus 1 yn plus 1 predicted, which is the value of the function at xn plus 1 yn plus 1, because we know what is f of x comma y. So, once we know what the function here is, I can evaluate yn plus 1. That is going to be a value that I get for yn plus 1, which is obtained using the predicted value of yn plus 1. So, I have essentially corrected the value of yn plus 1. So, I call this as a corrected value. So, I now have two methods with the help of which I am able to predict yn plus 1. So, I call this method as a predictor method, and using that predicted value here I am able to correct it, and so I call this as a corrector method. Euler's method and modified Euler's method serve as a predictor-corrector pair for computing the solution of an initial value problem of the form dy by dx is equal to f of x comma y and y of x naught is y naught, and one will be able to obtain the solution at the next point knowing the information at a previous point. So, this suggests that more efficient methods can be devised by employing predictor-corrector methods, so that whatever that is predicted can be corrected and successively recorrected till the desired degree of accuracy is attained. So, in this class we shall look for some more predictor-corrector methods. So, we shall look into So, we will derive some predictor-corrector methods in this class, which help us to solve dy by dx is equal to f of x comma y, given that y of x naught is equal to y naught. If suppose we have information about the solution of this problem at points say x naught, which is given by this initial condition, at x1, x2, x3, and if you are asked to compute the solution say at x4, which means the solution at the point x4 makes use of the information at the previous 4 points, namely the solution at x4 is y4, and that is what is needed by us. So, the solution at x3, x2, x1 and x0 are given to us. With this information, we should find out what y4 is. So, the computation of solution at y4 involves the knowledge of the solution at the previous points. So, the methods that we derived by requiring that information is needed at a set of previous points in order to obtain the solution at this point, then such methods are called multi-step methods. So, essentially we will be deriving what are referred to as multi-step methods. Once we derive them, we can conveniently use these methods as predictor-corrector methods and obtain the solution of the given problem correct to the desired degree of accuracy. So, let us first derive what is known as Adams-Moulton predictor-corrector method. So, it solves a differential equation dy by dx is equal to f of x comma y. Let me integrate both sides with respect to x from xn to xn plus 1. So, dy by dx into dx will be integral xn to xn plus 1 f of x y integration with respect to dx. So, this tells you y at xn plus 1 minus y at xn is integral xn to xn plus 1 f of x y dx. So, at this stage I shall approximate the function f of x comma y using Newton's backward interpolation polynomial. So, f of x comma y is fn plus p into delta fn plus p into p plus 1 by factorial 2 into del square fn plus p plus 1 p plus 2 by factorial 3 into del cubed fn plus p plus 1 p plus 2 p plus 3 by factorial 4 into del power 4 fn plus etc. So, by fn I mean the value of the function at xn yn, and by p I mean x minus xn divided by h. So, I substitute for f of x comma y here. So, I get y of xn plus 1 minus y of xn is integral xn to xn plus 1 f of x comma y. So, fn plus p delta fn plus p plus 1 by 2 into del square fn plus p plus 1 p plus 2 by 6 del cubed fn p plus 1 p plus 2 into p plus 3 by 24 into del power 4 fn plus etc. integration with respect to x. Now, I observe that the variable here is p and the integration is with respect to x. So, I use this transformation. So, I have x minus xn to be h into p. So, dx will be equal to h dp. Further, when x is equal to xn, then this tells that p is 0, and when x is equal to xn plus 1, then we have h to be equal to hp, which gives you p to be equal to 1. So, the integration is h times integral 0 to 1 Fn plus p delta Fn plus p plus 1 by 2 del square Fn. So, I write down all these terms as they are and then perform the integration. Integration is now with respect to p. So, the first term will give you h into Fn dp integrated with respect to p from 0 to 1. So, it is Fn into p between 0 and 1. So, it is simply Fn. The second term p dp, so p square by 2 between 0 and 1. So, half of delta Fn, then plus half of p into p plus 1. So, that will give you p square plus p, and that has to be integrated with respect to p. So, that will give you p cube by 3 plus p square by 2 between 0 and 1. So, this will give you 5 divided by 6. So, this term will give you 5 by 12 into del square Fn. Then the next term p into p plus 1 is p square plus p, and that has to be multiplied by p plus 2. So, that will give you p cubed plus p square plus 2p square. So, this will become 3p square plus 2p. So, I have to integrate this between 0 and 1 with respect to p. So, that will give you p power 4 by 4 plus 3 p cube by 3 plus 2 p square by 2 between 0 and 1. So, this gives you 1 by 4 plus 1 plus 1. So, we have 9 by 4. So, I have already 6 here. So, 9 by 24 into del cubed Fn, and then I have to perform integration of this term. So, let us work out the details. So, I have p plus 1, p plus 2 given by p cube plus 3p square plus 2p. So, we have p cubed plus p square plus 2p. Now, that has to be multiplied by p plus 3. So, and that will give you p to the power of 4 plus 3p cubed plus 2p square, and then plus 3p cubed plus 9p square plus 6p, which will give you p power 4 plus 6p cubed plus 11p square plus 6p. Now, I have to integrate this with respect to p, and that gives you p power 5 by 5 plus 6p power 4 by 4 plus 11p cubed by 3 plus 6p square by 2 between 0 and 1. So, let us substitute for p the upper and the lower limit. That gives you 1 by 5 plus 6 by 4 plus 11 by 3 plus 6 by 2. So, if you evaluate this, then you get 502 by 60. So, I substitute here, that will give you 502 by 60 into 1 by 24 into del power 4 Fn. So, I shall truncate this terms here at this stage. So, y of xn plus 1 minus y of xn, which is this, when the integration is performed, gives you this result, which can be simplified. So, and it is given by h into Fn plus half delta Fn plus 5 by 12 del square Fn. Then the next term 3 by 8 into del cubed Fn plus this gives you 251 by 30 into 24. So, that is 251 by 720 into del power 4 Fn. So, let us now substitute for the backward differences delta Fn, del square Fn, etc., and then express this in terms of the function values. So, we obtain y of xn plus 1 minus y of xn is given by h. Let me rewrite that expression once again, then it will be easier for me to make the computations. So, Fn plus half delta Fn plus 5 by 12 into del square Fn plus 3 by 8 into del cubed Fn plus 251 by 720 into delta power 4 Fn. So, we use the definition of the backward difference operator on Fn. So, that gives you Fn minus Fn minus 1. So, what is del square Fn? It is the backward difference operator operating on Fn minus Fn minus 1. So, it is delta Fn minus delta Fn minus 1, and that is Fn minus Fn minus 1 minus Fn minus 1 minus Fn minus 2. So, that will give you Fn minus 2 Fn minus 1 plus Fn minus 2. That is what is del square Fn. We require del cubed Fn. So, that will be Fn minus 3 Fn minus 1 plus 3 Fn minus 2 minus Fn minus 3. And finally, we have del power 4 Fn, and that will be Fn minus 4 Fn minus 1 plus 6 Fn minus 2 minus 4 Fn minus 3, then plus Fn minus 4. So, we have obtained the backward differences on Fn which appear here and express them in terms of the function values at different points. So, now we have to substitute these here and collect the like terms and then write down the result finally. So, we have the first term to be Fn, the second term is half of delta Fn, which is Fn minus Fn minus 1. Then the next term is 5 by 12 into del square Fn, that is Fn minus 2 Fn minus 1 plus Fn minus 2. Then I have 3 by 8 into del cubed Fn. So, that gives you Fn minus 3 Fn minus 1 plus 3 Fn minus 2 minus Fn minus 3. And finally, this term 251 by 720 in. So, we shall retain that term as it is, as del power 4 into Fn. I do not want to substitute that in terms of the function values. Let us simplify these terms. So, I shall collect the terms involving Fn. So, the first term has coefficient 1, then we have half, 5 by 12, then 3 by 8. That is the coefficient of Fn. And then the next term is Fn minus 1, minus half, which comes from this, then minus 10 by 12 from this term, then minus 9 by 8. Then I collect the terms involving Fn minus 2, that is 5 by 12 from there, and then 9 by 8 from the next term, and we have Fn minus 3, whose coefficient is minus 3 by 8. And I have the next term, which is 251 by 720 into del power 4 Fn. So, we have to simplify these. So, I shall take say 24 plus 12 plus 10 plus 9. So, 36, 46, so 55 by 24. So, coefficient of Fn is 55 by 24. Then I have minus Fn minus 1 into, so I shall now take 24 as common denominator. So, I have 12 plus 20 plus 27, 47, 49, so 59 by 24 into Fn minus 1. Then this term again 24, so 10, 27, so plus 37 by 24 Fn minus 2. And then if I take 24 here, then it will become 9 by 24 Fn minus 3, and then the last term 251 by 720 into del power 4 Fn. So, we have simplified the right hand side. So, we write down the result. Therefore, y of xn plus 1 is equal to y of xn plus, I have h as a coefficient here. So, h by 24 into Fn minus 59 Fn minus 1 plus 37 Fn minus 2 minus 9 Fn minus 3 plus 251 by 720 into h into del power 4 Fn. Thus, we have y at xn plus 1 to be given by y at xn plus h by 24 into a linear combination of the function values f of x comma y at xn yn. This is at xn minus 1 yn minus 1, xn minus 2 yn minus 2, and this is at xn minus 3 yn minus 3. And this was obtained by approximating the function f of x comma y by means of backward interpolation polynomial for equally spaced points. So, the result that we get is an approximation value to y of xn plus 1. So, we denote it by yn plus 1, and that is yn plus h by 24 into 55 Fn minus 59 Fn minus 1 plus 37 Fn minus 2 minus 9 Fn minus 3 plus 251 by 720 into h into del power 4 Fn. So, what does this method indicate? Suppose you require the solution at this point xn plus 1, namely yn plus 1 is what you have to find. Then you require the knowledge of the value at xn, which is yn, and what about this? Fn is f of xn yn. So, when you know what is yn at xn, then you can compute what is f of xn yn. So, this term is known. What is fn minus 1? It is f of xn minus 1 yn minus 1. So, the information at the previous point, namely xn minus 1, should also be available to you, and you call that as yn minus 1, and once you have this, you find what fn minus 1 is. Similarly, you compute the values of fn minus 2, which is f of x minus 2 yn minus 2, and fn minus 3, which is f of xn minus 3 yn minus 3. So, that is going to be obtained by using the information at xn minus 3, where the solution is yn minus 3. So, in order to get the solution at xn plus 1, you require information about yn at the previous 4 points. So, essentially what is it that you have done? You have approximated that function f of x comma y by a polynomial passing through these 5 points xi, yi, such that this will be a 4th degree polynomial, and hence the 4th order backward difference is constant, and the 5th and the higher order backward differences are all 0, and that is why you truncated your Newton backward interpolation polynomial at the term which contained del power 4 fn. Question now is, how do you get these values? Because your problem is dy by dx is equal to f of x comma y, and you will be given information at some initial point x naught, y naught. You are asked to compute the solution at xn plus 1. So, you require the knowledge of the solution at the previous 4 points xn, xn minus 1, xn minus 2, xn minus 3. Divide the interval x naught to xn plus 1 into 4 equal parts and name those points as xi, and then try to obtain the solution at other 3 points using single step methods which you have already learnt. Namely, you can use Euler's method or Taylor's series method or Runge-Kutta method of order 2 or order 4 and compute the solution at the points at which you require the information. So, step 1 would be to collect information at a set of previous 4 points. Once you have that information, now use this method to obtain the value of y at xn plus 1, which is denoted by yn plus 1, because you know now every value with the help of the information that you have computed, and hence you can compute yn plus 1. So, this is a multi-step method, because the value at xn plus 1, which is yn plus 1, is obtained by having information or knowledge about the solution at the previous points, which can either be given to you a priori, or you will have to compute using the single step methods which you have already learnt. And using those information at the previous points, you can use this method and compute what yn plus 1, which is the value of y at xn plus 1, and it is an approximation to the value of y at xn plus 1. So, it is a multi-step method. Now, we shall derive another multi-step method, which the calculations, the argument and the discussion are analogous to this. So, I will not be doing in detail these calculations. I will just indicate the method and present what finally the method is, and then tell you how we can use the method that we have derived now and the one that we are going to derive now can be used as a predictor-corrector pair, and solution to a particular problem can be obtained correct to the desired degree of accuracy. Here P is x minus xn plus 1 by h. This gives you dP into h is dx. So, when x is xn, you have xn minus xn plus 1 to be hp. So, minus h is hp, so p is minus 1. When x is xn plus 1, then this gives you p equal to 0. So, the limits of integration are p is equal to minus 1 to p is equal to 0 of the terms within this bracket, and integration is now with respect to p. So, you have to work out the details of this integration. I shall give you the result. So, we have y of xn plus 1 will be equal to y of xn plus h by 24 into 9 fn plus 1 plus 19 fn minus 5 fn minus 1 plus fn minus 2 plus minus 19 by 720 times h into del power 4 fn plus 1. And since we have approximated the function f of x comma y by means of backward interpolation polynomial about xn plus 1, we obtain an approximation to the value of y at xn plus 1. So, we have yn plus 1 to be given by yn plus h by 24 into the terms which are written here. So, let us look at this method that we have derived. Again we observe that it is a multi-step method. It requires the knowledge of the solution at xn, which is yn, at xn plus 1, which will be yn plus 1, only then we can compute what fn plus 1 is. Namely, fn plus 1 is f of xn plus 1 yn plus 1, and we already have seen fn is f of xn yn, fn minus 1 is f of xn minus 1 yn minus 1, and fn minus 2 is f of xn minus 2 yn minus 2. Now, we see that the left hand side gives you yn plus 1, and on the right hand side we have fn plus 1, which requires the knowledge of what yn plus 1 is. We are only trying to get what yn plus 1 is, but that involves the knowledge of yn plus 1 in getting fn plus 1. From where do we get it? We make use of the yn plus 1 that we already derived in the earlier method. Recall, this is the method that we had derived earlier, where we are able to write down what yn plus 1 is when we have information at a set of previous points. So, we use this yn plus 1 obtained using this method in evaluating what fn plus 1 is. Then we know what fn plus 1 is. Of course, the other values can be computed with the available information. So, we obtain the value of yn plus 1. This is the second time that we get yn plus 1 at xn plus 1 for the same problem governed by the differential equation. we used the method which we derived earlier to get yn plus 1, that is used here, and in turn fn plus 1 is used here, and that gives you a new value of yn plus 1. So, we say that we have corrected the value of yn plus 1 by the new method that we have derived, and this was done by using the yn plus 1 obtained by the earlier method as a predicted value. So, I call this as a predictor and the method that we have obtained now as a corrector. So, how do I get fn plus 1? It is f of xn plus 1. This yn plus 1 is nothing but the predicted value obtained from the predictor. So, thus we have a predictor-corrector pair. For solving an initial value problem, dy by dx is equal to f of x comma y. So, let us write down what the corrector is. This is given by yn plus 1 corrector is this expression. So, my predictor is this and my corrector is going to be this. Again I observe that the last term gives me the local truncation error in this multi-step method. Another observation, just look at the local truncation errors in both the methods, right. So, you observe that the local truncation error in the predictor method is several times that in the corrector method, and therefore, the error that is incurred by using this method in predicting the value of yn plus 1 is corrected using the corrector method. In addition, the corrector method can be used successively to recorrect our solution till the desired degree of accuracy is attained. How do we do it? We are given a problem dy by dx and we are given enough information that is required to compute yn plus 1 using the predictor. Once the predictor is obtained, we use it here and correct it. At this stage, we check whether the difference in absolute value between the corrected value and the predicted value is less than epsilon, which is the desired degree of accuracy. So, let us write down the details. So, what do we do at this stage? At this stage, we check whether yn plus 1 obtained using the corrector minus yn plus 1 obtained using the predictor is less than epsilon. If so, then we stop and then take this yn plus 1 corrected value as approximating y of xn plus 1. Stop and take the solution as approximating y of xn plus 1, which is given by yn plus 1 corrected value. If suppose this does not happen, then what do? You use the corrector once again and get the second corrected value. How do you use it? The second corrected value is going to be yn plus h by 24 into 9 into fn plus 1 plus 19 fn minus 5 fn minus 1 plus fn minus 2 plus the truncation error minus 19 by 720 h into del power 4 fn plus 1. Here the fn plus 1 is going to be f of xn plus 1 yn plus 1, but which yn plus 1 will you use? You have a first corrected value there, that is what you are recorrecting. So, you compute yn plus 1 double corrected value by evaluating fn plus 1, making use of the first corrected value of yn plus 1. The rest of the terms will be the same, there will not be any change. The only change that will occur in this will be at fn plus 1, which is now f of xn plus 1, yn plus 1, first corrected value. What do you do now? You check whether yn plus 1 double corrected value minus yn plus 1 first corrected value is less than epsilon. If then, stop. If not, continue this process. If not, continue recorrecting your solution every time computing what is fn plus 1 by making use of the value of yn plus 1 obtained at that corrected step, and then evaluate the new yn plus 1, which is the corrected value, till the desired degree of accuracy is attained. So, if not, continue till the desired accuracy is attained. So, the predictor-corrector method helps you to obtain the solution of dy by dx is equal to f of x comma y, correct to the desired degree of accuracy by using the predictor. You predict the value and then you can successively recorrect using the corrector till the accuracy is attained. So, I am sure you have been able to understand the details in the derivation of this predictor-corrector method. This pair, the predictor and the corrector together, is known by Adams-Moulton predictor-corrector method, or it is also called a predictor-corrector pair. Let us illustrate Adams-Moulton predictor-corrector method for solving a differential equation. So, consider the differential equation dy by dx is equal to y minus x square, and the information given to you is y of 0 equal to 1. The question is, find the solution of this initial value problem at x is equal to 1 by taking step size as 0.2. So, we are given the solution at 0 in the form of an initial condition. So, this is x. If I call this as say x naught, y of x naught is y naught, and that is given to be 1. And I require the solution at 1, and I am asked to go in steps of h, which is 0.2. So, let us mark these points 0.2, 0.4, 0.6, 0.8 and 1, and I am asked to use Adams predictor-corrector method. So, I can compute the solution yn plus 1 and predict it if I know information at xn, xn minus 1, xn minus 2, xn minus 3. So, I require information at 4 points. So, I have information given here. So, if I know information at these 4 points, then I can evaluate the value at this point using the predictor. So, in step 1, I shall denote this by xn plus 1. So, 0.6 will be xn, 0.4 will be xn minus 1, 0.2 is xn minus 2, and 0 will be xn minus 3. And therefore, what is the corresponding value of y? It is yn minus 3. since xn minus 3 is 0, yn minus 3 is 1. That is already given to me. So, I need to now get the solution at these points 0.2, 0.4 and 0.6. Only when I have information at all the 4 points, I can use the predictor and get the solution at this point, and then use the corrector to correct it. So, my goal now would be to compute the solution at 0.2, 0.4 and 0.6. So, step 1. So, given a problem, write down what are all the information that you gather from the given problem and what is it that you require. That is your first step. And then continue in your first step the computation of whatever that is required. So, we require solution at 0.2, solution at 0.4 and at 0.6. So, how do you get this? These solutions can be obtained using, say, Runge-Kutta method of order 4. How do you do it? You know the solution at this point. So, I march one step ahead and compute the solution by Runge-Kutta method at this point. Isn't it? What is it? So, I require y at 0.2. What does Runge-Kutta method of order 4 says? It says it is y at 0 plus plus 1 by 6 into k1 plus 2k2 plus 2k3 plus k4. What is k1? K1 is h into f of x naught, y naught. So, 0. What is y naught? It is 1. And what is k2? K2 is h into x naught plus h by 2, y naught plus k1 by 2. And k3 is h f of x naught plus h by 2, y naught plus k2 by 2. And finally, k4 is h f of x naught plus h, y naught plus k3. So, I know what the function is that is given to me. What are x naught, y naught, which are 0 and 1. So, I can compute k1, k2, k3, k4, substitute here and arrive at what y at 0.2 is. So, once y at 0.2 is obtained, then again I use Runge-Kutta method of order 4. I march one step ahead and find the solution at 0.4, and that is y at 0.4. I do the same thing and obtain the solution at 0.6. So, please carry out the details of these computations. I will give you the results, namely the values at these points, and then we move on with using the predictor-corrector method to obtain the solution at 0.8. So, it's when we do it by Runge-Kutta method, we get y at 0.2 to be given by 1.21859. Y at 0.4 is given by 1.46813. Y at 0.6 is 1.73779. And we already know that y at 0 is 1. So, we have the solution obtained using Runge-Kutta method of order 4 at these 3 points, and this is an initial condition that is given in the problem. So, we have information at all these 4 points which is needed to obtain the solution at the point 0.8 using predictor method. What does the predictor method say? This is a predictor, that is yn plus 1. So, I have called this as my xn plus 1. So, the value of y at this point is what is denoted by yn plus 1. So, yn plus 1 predicted will give me y at point 8 according to my notation, and that is equal to y at n. What is yn? It is going to be y at point 6 and then plus h by 24 into 55 times f of, what is fn? It is f of xn comma yn. xn is 0.6. What is yn? We have just now obtained its value, that is 1.73779. Then the next term, minus 59 into f of, what is fn minus 1? It is xn minus 1, yn minus 1. So, it is f at 0.4 comma, what is yn minus 1? We have computed it to be 1.46813. Then the next term is 37 fn minus 2, and fn minus 2 is f of xn minus 2, yn minus 2. So, it is f of 0.2 comma, what is the value at 0.2? 1.21859, and the last term minus 9 times fn minus 3. Our n minus 3 is 0 and the value there is 1. So, it is f of 0 comma 1. So, it is always better to write down using the formula what is it that you want, and then evaluate these functions at these points and then simplify to get the answer. So, let us find out what is f of x comma y. The problem tells you that f of x comma y is y minus x square. So, you require f at 0.6, 1.73779. So, it is 1.73779 minus x square. So, 0.6 square. Then f at 0.4, 1.46813. So, it is 1.46813 minus 0.4 square. F of 0.2, 1.21859. So, 21859 minus 0.2 the whole square, and f of 0, 1, and that will be 1 minus 0. I substitute these values in this formula, and that gives me y at 0.6, which is 1.73779, h is 0.2 by 24 into 55 times f of 0.6, 1.73779, which is this value, and I have to take 55 times this value, and that turns out to be 75.77845. The next value is 77.17967, then 43.60783, and finally we have minus 9. And if you simplify this further, it turns out to be 2.01451. So, this is your y at 0.8, and that is what is predicted. Having predicted the value at 0.8, we would like to correct it using the corrector. So, before using the formula, just find out what is this fn plus 1. What is fn plus 1? Here fn plus 1 is going to be f evaluated at x comma y. What is x? It is 0.8. What is y? Y is y of 0.8, that is predicted. So, it is f at 0.8, 2.01451, but f of x comma y is y minus x square. So, 2.01451 minus 0.8 the whole square. So, compute that Fn plus 1 first. Let us now use the corrector and write down the corrected value. So, yn plus 1 corrected is y of 0.8 corrected value, and that is equal to yn, which is 1.73779 plus 0.2 by 24 into Fn plus 1, which is this, and that turns out to be 12.37059. Then the next term is 19 times Fn, which is 26.17801. Then the third term minus 5 Fn, that is 6.54065, and finally plus 1.17859, which is Fn minus 2, and that turns out to be 2.01434. This is the corrected value of y at 0.8. The predicted value is 2.01451 and the corrected value is 2.01434. If I require that my solution is correct to 2 decimal places, I observe that the predicted value is 2.01 and the corrected value is also 2.01. So, the desired degree of accuracy is attained at this step. That is not the end of the problem. What is it that we want? We require the solution at 1. The question is compute the solution at 1. So, what does that mean? We require the solution at 1. So, I should call this as xn plus 1. In order to obtain solution at xn plus 1, which is 1, we require information at the previous 4 points and they are all available. The value at this point was just now computed using the predictor-corrector method. And so, we again work out the details as before. Use the predictor and predict this value and then successively use the corrector and obtain the solution correct to the desired degree of accuracy. So, I leave this as an exercise. I will give you the answers. You can work out the details yourself. The predicted value turns out to be y at 1 predicted turns out to be 2.28178. I can give you the step just before the final answer so that you can check the details yourself. Y1 predicted value is 2.01434 plus 0.2 by 24 into 75 plus 0.5887 minus 81.28961 plus 48.40081 minus 10.60731, and that turns out to be 2.28178. That is what I had given. Now, I would like to correct this value using the corrector. That requires information of f at this point. So, f at xn plus 1, yn plus 1, that is y1 predicted is required, and I also have to multiply it by 9 in the formula. So, I take 9 times this and the value turns out to be 11.53602. Once I have the fn plus 1 value, I use the corrector. So, yn plus 1 corrected is y at 1 corrected, and that turns out to be 2.01434 plus 0.2 by 24 into 11.53602 plus 26.17801 minus 6.54065 plus 1.17859, and the result is 2.28393. So, this is the corrected value at 1, and the predicted value at 1 is 2.28178, and we observe that if we demand 2 decimal place accuracy, then the difference between the solution of the corrected value and the predicted value is less than the prescribed tolerance, and so we have been able to obtain the solution correct to the desired degree of accuracy, namely 2.28. So, in the next class we shall derive another predictor-corrector method, which is known as Milne's predictor-corrector method, and the computation details are analogous to what we have done here. In this case, in deriving Adams-Moulton predictor-corrector method, we approximated f of x comma y by using backward interpolation polynomial by Newton, whereas in Milne's predictor-corrector method we shall approximate f of x comma y, say by using forward interpolation polynomial by Newton, and obtain a predictor-corrector pair known as Milne's predictor-corrector pair. So, we shall continue our discussion about this predictor-corrector method in the next class.